Good afternoon, everyone. We're just allowing a bit of time for everyone to dial into this webinar. But for those who already are here, I would like to welcome you this afternoon to another webinar in the webinar series of RTE Europe, where we will educate you on the basics of UV and EV technology. And we have 2 more webinars this week, but today we're going to talk about equipment. And for that, we have Romain, who will be presenting the webinar today. If you have any questions, then please feel free to enter them in the Q&A section, and we will deal with them afterwards. Go ahead, Romain.
Okay, thank you, Elke. Good afternoon, everybody. So yeah, today we are going to speak about the equipment for UV or electron beam technology for this webinar series. So let's start with the energy curing definition. It's a transformation of specifically formulated liquids into solids by use of the UV light or electron beam. And this kind of technology have main advantages. It's almost instantaneous, mainly solvent-free, so which can also allow you to reach higher production rates. The chemistry is stable at the one-component system. We are in a low or so we could say eco-energy technology compared to infrared or heat varying solution. As we have no solvent, we are also we have less dangerous waste products, and we have a, let's say, eco-friendly solution. So what happens when we have a UV or electron beam curing process? So we turn a liquid formulation into solid. You can see that on the left drawing, thanks to UV light or electron beam solution. So just to jump on some fact about general equipment parameters that we have to consider for the formulation, for the chemistry itself. About the construction, metals or other than stainless steel may catalyze the polymerization process. About the pumping, some friction causes locally high temperatures, which may lead to seed some area with polymerization of the formulation itself. The packaging is also very important to consider. So black PE containers keep the light out, but also allow the passage of oxygen. And we know that the oxygen has a mild stabilizing effect on radiation curable formulations. And about the shelf life, UV or EB for electron beam curable products can have a shelf life of only 6 months. And with correct stabilization and storage, this can be increased to about a year or more, depending on the formulation itself. Also, something very important is to avoid equipment with dead volume. Polymerization may occur in these spaces and also lead to seed polymerization of the product itself. Then if we speak about the parameters of the process that has to be considered, when processing or storing, we should never exceed the 45 degrees Celsius when the batch contains monomer or oligomers or photoinitiators. The use of short-term hotbox storage for high viscosity oligomers in order to achieve a lower viscosity for better handling. If we keep the hotbox times as short as necessary and temperature as low as functionally possible. Photoinitiators or eutectic mixtures may be kept in their liquid state for long-term storage in containers at temperatures up to 60 degrees without losing any of them different characteristics. We have to to be careful, shade sunlight completely away from the processing and converting areas of the UV or electron beam curing formulations. The ambient daylight or also light coming from ordinary fluorescent lamps you can have in the area may also cause unwanted polymerization of your formulation. And so in this case, we must keep light source distant enough or install light filters to avoid that kind of issue. About the handling, UV or electron beam products are not flammable or corrosive. They are mild skin irritants, and the major handling precaution is to avoid skin and eye contact during using the correct gloves, eye protection, and suitable clothing. And if there is by any unluck contact, you just need to wash it with the soap and water. And about the cleaning, it's only cleaning solvents suitable for UV or electron beam products that can be easily asked to the formulation supplier. Remember that the formulation only cure in the converting process. So thanks to the UV or electron beam, and any spillage with equipment, floor, wall, clothing, or even cleaning rags, the spillage will remain wet without any UV or electron beam on it. Now, if we jump on the radiation equipment itself, we have to take into consideration three main key elements. For the first one is the total UV energy. So the unit is the joule per square centimeter. So it represents the total amount of photons received by your coating during your process. And it is so highly linked to the speed of the line. So it's something inversely proportional to speed. We'll see that into more deeply. We have also to take into consideration the peak irradiance, which is in watt per square centimeter. So this represents the flow of photons per second going through your coating surface. So we have a big link between the irradiance in watt per square centimeter and the joule and the energy in joules per square centimeter, which is the time and so the speed of the line. And this peak irradiance is highly dependent on the type of your lamp, the type of your system, the geometry of the lamp, the geometry of the reflectors, and the geometry of the construction of your UV or electron beam equipment itself. And this peak irradiance, as it is the instantaneous power, is completely independent of the speed. And last but not least, we have to first take into consideration the spectral output of the lamp, the bulb, or the LED, which is the wavelength distribution of it, because each photons have a different characteristics. So we know well about the UVA, UVB, and UVC, and this has to be taken into consideration when we deal with an energy curing process. So now we'll go a little bit deeper into these three different key elements. So if we start with the total UV energy, which is in joule or millijoule per square centimeter. So this energy is, of course, proportional to the lamp power. On the left, you can see you have two curves, one with a lamp of 120 watt per centimeter in blue, and in red, you have one which is 2 times more powerful at 240 watt per centimeter. And if we take, for example, a speed of 10 meters per minute, you can see that with the first lamp at 120 watts per centimeter, you reach a total energy of 500 millijoule per square centimeter. Compared to a 2 times more powerful lamp, you reach 2 times more energy, so you get 1000 millijoule per square centimeter. So you have energy proportional to the lamp power, but you have also the energy proportional to the number of lamps, so the row of lamps. That's quite easy to imagine. If you put 2 lamps next to each other, you will allow the coating to receive 2 times more photons, and so 2 times more energy. And like I said previously, the energy is inversely proportional to the line speed, which is also quite easy to imagine, because if you increase your speed, you will decrease the time that the coating has below the UV, and so the total amount of photons received by your coating line, by your coating formulation. So that's about the UV energy. And this UV energy is something, when we have to define a UV or atomic, is something we have to take into consideration. So with this information and the speed of the line, we have already a good idea about which power of lamp we need to use, and also the number of lamp we need to integrate into the system. Then we can jump on the peak irradiance, or the irradiance of the UV lamp, which is the instantaneous flow of photons going every seconds through our coating. On the left, you have the black curve represents the irradiance profile of one lamp. So it's the output distribution of light over your surface. And this irradiance profile allow us to have also a good idea of the total energy that could be received by the coating, thanks to the integration of it. So when we take the area under this curve, we can have a good idea of the total energy that will be provided by our UV sources, taking into consideration the speed of the line also. And this irradiance, or this irradiance profile, is highly linked to the geometry of the lamp, and also to the distance of the lamp between the lamp and your coating. On the drawing on the right, you have a curve representing the peak irradiance in watt per square centimeter in the vertical axis, decreasing as we increase the distance between the lamp and the coating. And so that's something we have to also take into consideration when we define which system would be suitable for a certain application. And so we can, looking at energy and in irradiance, we can ask ourselves about, okay, if for the same energy, so for the same amount of photons, do we have the same impact if we reach this energy with a very powerful lamp in a very short time, or with a very low powerful lamp in a very long time? That's an important question, and we know that the higher intensity, the intensity of the light at the surface, the higher the intensity of the light at any point within the depth of the coating. And so this has several positive impacts, like we have a greater depth of penetration of the UV. And so thanks to that, we improve the cure at the substrate coating interface, which is the more depth zone for the curing application. Thanks to that, we increase the adhesion to the substrate, because we have a better degree of cure close to the substrate. And on the right, you can have an example of that. So if we take on the first line, if we take a lamp of 120 watt per centimeter lamp, we pass one time below it. So the lamp has an irradiance of 3,200 milliwatt per square centimeter. Let's say that one passage through the lamp is equal to 1 second. So with 1 second of irradiance of 3,200 milliwatt per centimeter, you reach a total energy of 3,200 millijoule per square centimeter. And so with this lamp, we measure a depth of cure of 25 micrometer. Now let's say, okay, I want to increase my energy, so I go 2 times under my 120 watt per centimeter lamp. So I go 2 times behind it, so with the same irradiance, but as I'm going 2 times below it, I have an energy which is doubled compared to the first line. So I have energy of 6,400 millijoule per square centimeter. And with this energy, I'm able to increase a little bit the depth of cure of my formulation up to 35 micrometers. But no, if for the same energy, so if I'm going to the third line, so I'm taking a lamp which is 2 times more powerful. I'm going behind it only 1 time. The irradiance is 6,400 milliwatt per square centimeter, so 2 times the irradiance of the previous lamp. So I have a higher intensity. At the end, my energy is equivalent to the second line. I have 6,400 millijoules per square centimeter. But as for the same energy, I had a higher irradiance, so my locally my photons were able to go deeper in my substrate. I reached a target, a depth of cure of 50 micrometers. So that's something we have to take also into consideration when we define a process. It's not because you have the same energy that you will get the same results at the end of your process. It's also linked to the irradiance, so that these two specifications have to be taken into consideration when you define when you want to define the right UV equipment. Then the last one is the spectral output, so the wavelengths of our UV equipment. We know that when we speak about the UV mercury medium pressure lamp, depending on the doping of our lamp, we are able to shift the spectral outputs, and also in order to match better with the formulation of the coating itself. So here you have an example of some classical spectral output for mercury lamp. You have on the top, you have classical mercury lamp. On the bottom left, iron doping lamp, and on the bottom right, gallium doping lamp, for example. So thanks to some doping, we are able to shift and to move the wavelengths output of our mercury lamp, again, in order to match with the needs of the coating application. And now if we go, as we saw, the 3 main key elements that we have to take into consideration for a UV or electron beam application, we can have a look at the 3 main technology that allow us to provide some UV radiation curing. So we have the UV medium pressure mercury lamp, we have the electron beam, and the UV LED. So I will go a little bit deeper into the 3 of them. If we start with the UV medium mercury pressure lamp, we have a quartz body with 2 electrodes on both sides, which allow some electricity to go through the lamp. So the quartz itself is containing some inert atmosphere, so some inert gas in which we had some mercury, a specific volume of mercury. And before turning on the lamp, we hit and we put some power on the both electrode, so that the mercury is becoming a gas into our lamp. And then by increasing the voltage on the two connectors, we create an arc. We call that an arc, which excites the mercury molecules, and this mercury molecule then creates the UV light. So that's a way to create UV. One of the first way we found in order to create UV light for our application. Then we have the electron beam unit. So the electron beam sources deliver highly energetic X-ray emission. So the wavelength is below 10 nanometers. When we have a mercury lamp, we have wavelengths between 200 nanometers and let's say 500 nanometers. So here we have very, very low nanometer wavelengths with high energy. Because of this wavelengths, the electron beam unit has to be built around an inerted atmosphere. So you can see that on the left drawing. It's needed in order not to absorb all of the photons. This kind of photons at 10 nanometers are highly reactive and mainly absorbed by the oxygen in the atmosphere. So for this kind of application, we need to inert the area around the generator, so the electron beam and the tungsten filament and the coating line. Thanks to this highly powerful photons, the electron beam allow radical formulation without radical formation without photoinitiators. There are no infrared radiation and no heat exposure of the substrate, which could be also an advantage depending on the application you have. And third, we have the UV LED lamp. So the UV LED, the LED is for light emitting diode. It's a solid state device that produces light. So it's let's say different materials stacked, and depending on which depth of material you have, you're able to change the wavelengths of your diode, and then by thinning through it some electricity, some electrons, you can excite the molecule, the atoms, and again by this excitation they will release some UV. And then this different chip, so we can also call the LED some chip, are packaged in different kind of arrays, and these arrays allow us to create a big enough surface of UV light in order to reach the needs of a polymerization process. So that's an example of the differences between the spectral output of a mercury lamp and LED. On the market, we have lots of questions about what are the main differences between LED and mercury lamp. Are the LEDs going to replace completely the mercury or not, etc., etc. But we have to take into consideration many things because the two technologies are quite different and allow us to reach different targets and different application process. So if we start with the LEDs itself, we have a almost monochromatic emission of UVA. So you have, for example, the purple curve, which is the emission of a 365 nanometers LED. On the market, we have also very often 385 nanometers or 395 nanometers or 405 nanometers wavelengths. So we can see that compared to the broad spectrum of mercury lamp, which is represented by the black curve, that we don't have the same amount of photons. We don't have the same, how do we say exactly? The same distribution of photons. With LED, we have quasi-monochromatic emissions, so we have to find formulation which fit perfectly with this kind of photons, which is not the case with mercury lamp. As it's broad, the formulation will sometimes always find a photon suitable for them to react. So that's the main difference. But a good advantage is also that the LED doesn't emit infrared radiation compared to mercury lamp. So again, we have no, or at least less heat exposure on the substrate itself. Yeah, that's it. Then we have also, by continuing on the spectrum, If we look at the chemistry itself, we see that there is a big dependence on the radiation itself. So here you have a curve of the different molecule bond we can try to break with the UV. So, for example, you have the TPO photoinitiators, which is into the red circle here. The energy needed to break these photoinitiators is around 450 nanometers. And if you look at the other photoinitiator or the other bond, you can see that sometimes you will need a higher energy, so which means a lower wavelength. So that's also a reason why sometimes we can't cure something with LED, which are emitting mainly in the UVA. So if you have a triple bond which require a wavelength of 150 nanometers in order to be broken, you can do that with only UVA. So that's why we need to take into consideration the formulation of the coating when we need to select the lamp and the technology of the lamp behind it in order to match the wavelengths emission and the wavelength sensitivity of our coating. The UV LED technology arrived quite after the mercury, so it started to take some market shares into the total radiation market. So, for example, in the printing industry, we have quite a lot of LED application right now, mainly at 395 nanometers. So, for example, in the wide format inkjet, also in the narrow format inkjet or rotatory screen. The flexo printing is quite well moving into the LED technology, and we see more and more LED technology in the offset printing. We'll see that to cure the inks, it's quite okay right now with the LEDs, but we face more and more challenges when we want to cure the varnishes after the ink because of some formulation of photoinitiator which are not suitable yet for LED curing. If we look at the adhesives application, when we need to glue some or to bond some electronic components in the smartphones or on the screen, on the display manufacturing, we can now have good formulation with LED technology. We see more and more medical devices sealants, medical devices, and also sealants for electronic devices with LED technology. If we look at the wood market, it's also increasing quite a lot. We see more and more development coming from the formulating company in order to allow the customer to cure the varnishes or with UV LED technology. And in the industrial coatings, for example, for optical fiber production or composite resin, repair composite resin, we see more and more LED formulation, which open new application, a new way of using the radiation technology in this kind of application process. And if we want to have a quick look of the advantages of the UV LED compared to the classical UV mercury technology, one of the first advantage is the lifetime. So the LED chips have a very good lifetime right now on the UVA spectrum. So we can say more than 15,000 hours quite easily. We also have some equipment able to reach a target of 30,000 hours of working, with only a decrease of the initial outputs of around about 25%. So that could have a good advantage compared to mercury lamp, the stability of the output during the time. Yeah, so the constant power output over a significant part of lifetime, which is quite good. We have a lower energy consumption compared to mercury lamp. I would say more efficient because with the LED, so if you put a certain amount of electrical energy, you will convert almost 30% in the UV spectrum, and 70% in the will be thermal losses. And if we speak about mercury lamp, we have something around about 20 to 30% of efficiency in the UV UV spectrum, but we have a lots of heat. We have ozone, which creates and which forces us to add additional components which also consume electricity. So at the end, with the LED, we can lower the energy consumption. Thanks to the geometry of the technology itself, so with the LED, we are able to define a system with more, with better uniformity, because if you put a uniform arrays of chip, you can reach a very good uniformity output compared to long bulb of mercury lamp. Another good point for this technology is the fact that you have no downtime due to the heating of the cooling period. So the LED is able to switch on and switch off instantly. We speak about milliseconds without creating any issue or any damage to the chip itself. Compared to a mercury lamp, that we know that we need to heat up the lamp in order to allow the mercury in it to become a gas, and then we can put the complete power in order to have the UV. And then we need, when we turn off the production, we need to have a time of cooling period. So that's a main difference that could be a good advantage for the LED. Then the LED don't create ozone. Mainly because they do not emit UVC, which is the main factors for the ozone creation. And so we don't need exhaust air and big tunnel on the top of the building in order to extract the ozone. And again, we have a lot less heat release and a lot less and no infrared radiation, which could be a very good advantages for certain applications. But this new LED technology, with this new technology, we'll also faces a lot of challenges. Of course, it would be too easy. First, about the working distance. So we thought that the working distance, as the working distance increases, the intensity of the UV decreases significantly. So it could create some issue when we need to define a solution in order to reach the total energy target. So it could be seen as the reduction of the speed of the coating line and so on. So because of that, some application may not be possible because of that. So we work on optimizing the UV LED lamp with micro optics, with different optical design in order to fight against this issue and to allow us to have more energy. The efficiency and the power that one LED is able to emit now is still increasing, and that will allow the system to reach the same amount of energy than a classic mercury lamp. But it won't do anything. because we have a limited choice of photoinitiators. And we see that with the classic UVA LED, we don't have the complete spectrum available. And so we can't take all of the photoinitiators available on the market. So as we have a narrow band emission LED, so we have a limited choices of photoinitiators, which limit the choices of the formulation, and so which limit the possibility of the application. So the power is not everything. We also have to think about the wavelength itself. Yeah, so we have to, the development is still coming, and so we need more new or more efficient photoinitiators in order to match with the LED output. We can also speak about reducing the wavelengths of the LED. That's something on which a lot of people are working on in order to try to emit more UVB and more UVC in order to try to replicate the spectrum of the mercury lamp. And yeah, again, because of the wavelengths of the LED in the UVA, we can have some challenge on the surface cure. So when we need a very hard scratch resistance closed surface, it's more complicated with LED because we don't have the UVC which are perfect in order to cure the surface of the coating. So that's another challenge. We can also face some tacky surface, again, because with the LED, we cure very well in depth because of the UVA. So the UVA is able to go deeply into the coating quite easily. So with the LED, we have no issue by curing in the depth of the coating, but the surface of the coating is a big challenge. Again, because of the main issue is the main reason is the wavelengths available with the LEDs. And so to fight this, we can make some application in inert atmosphere, but it's very complex, and it mainly increase the cost. We see lots of application where we mix the two technology, because all of them, the both technologies, LED and mercury, they have different advantages, and if we use properly the different advantages, we can, and if we mix them, we can have quite good application. So we can mix, for example, an LED in order to cure very deeply, and then a mercury in order to finish the curing also on the surface. That could be a kind of mix where we where the both technologies are used for a certain application. And then because of the LED, we need to select the right oligomers, the right monomers, and to make the right selection of the photoinitiators to overcome the different barriers as much as possible. We don't like to see to say that the LED will replace the mercury lamp. We have to you have to consider it as two technologies available with different advantages and different drawbacks, and depending on your application, one of the both or both of them will be suitable for your application. And in order to define this, it's quite important to understand quite well the differences between the two technologies. I think we're done with the presentation about the UV electron equipment. Thank you very much. If you want to stay up to date, you can have to link to the RTE website in order to see basically the two next webinars that will be tomorrow and after tomorrow. And if you have any question, feel free to ask it.
Thank you very much, Romain, for your very interesting presentation. So indeed, everyone, if you have any questions, feel free to enter them in the Q&A section. I did see one question already in our chat from Holger. It's which is the best lamp to cure flame retardant primer on pine due to the fact the flame retardant particles are very difficult to penetrate and cure.
Sorry, Elke, I lost you during the question.
Okay, yeah. If you want, you can also read it if you click on the chat, but I'll repeat.
If you have it on the chat, yeah.
Yeah. So the question is, which is the best lamp to cure flame retardant primer on pine due to the fact the flame retardance particles are very difficult to penetrate and cure?
Yeah. Well, that's hard to say without knowing the kind of primer you use. When you use a primer, you mainly want to cure in depth your coating. So depending on the formulation, I would say that a UV LED system, the UVA, would be suitable. But it's really depend on the formulation of your coating. So we need to take into consideration the photoinitiators itself in order to define properly the kind of lamp we can use.
Okay. All right. Then we have another question. Do you know any textbook which helps to learn the basics in this topic?
Yeah, I have quite of them in mind. Maybe best would be I need to look it down on the website, but I don't remember perfectly right now, but I can have a look. Yeah. Okay, I have some resources available if you want to go deeper into that kind of.
Okay, perfect. It was an anonymous question, but if this person would like to know, maybe it's best to send an email to us at mail@redtechstripeeurope.com, and then we can make sure to give you the titles. All right. The next question is from Ofelio. Do you recommend some of these technologies for different applicants? For example, for matte, anti-fingerprint, or exterior?
Yeah. So for matte anti-fingerprint, we have a kind of different UV lamp, which was not presented here during this presentation, as we were staying in the basics. But we call that the excimer lamp, which is a lamp emitting in the 220, it's 172 nanometers. So we are mainly in the UVC, and this lamp is able to cure interface and to create some microstructures in order to get this matte effect. And it's also a perfect solution in order to get some anti-scratch or anti-fingerprint varnish. So in general, we make a combination of excimer lamp in order to cure just this thin layer. So we speak about 100 nanometers in order to create this mattification effect. And then we use a mercury lamp in order to cure the complete coating. But again, that's something which was not presented in this webinar. But again, if you want to know more, you should contact us maybe later on in order to go deeply in that.
Okay. All right, thank you. And then there's another question from Matthias. It's about coil coatings. What do you think will be the predominant UV curing technology in the future of the coil coating process?
It's hard to see the future. Because we see many developments in the coil coating application. We see some combination of inert UV or with electron beam. Very hard to say, because it also depends a lot on what is the final products that will go out of your coil coating line. If you want something with a great resistance of corrosion, great anti-scratch resistance, and so on, you won't maybe use the same equipment and the same formulation if you don't want to. So we see more and more UV equipment and developments in this field. yeah, it's very hard to see in the future again.
Yeah, of course. All right, thank you. And then there's another anonymous question. I am considering which length is suitable to curing interior layers of UV resin system without cross-linking the outer layer.
So if you want to keep a sticky surface, for example, I would say that a UV LED technology would be easier because you will be able to select one wavelength in order to cure in depth by reducing the maximum amount of impact on the surface. So in that case, you can use the advantages of the UV LED for that. Yeah, and maybe by putting more oxygen, because we know that the oxygen is inhibiting the polymerization process. So if you want to have more curing in depth than in the surface, if you have a high oxygen area around it, you will limit the reaction on the top without limiting it too much on the bottom. So that could be a way. But I would start with LED, because with the mercury lamp, you will cure quite equivalently the same amount, the complete depth of your coating.
Perfect. All right, thank you very much. I see that we are at the end of the webinar now. There's one more question from Hossein asking if we can have the slides. The webinar has been recorded, so you can always listen it back on the on the RTE Europe website. But I guess we can also send a copy of the slides if you want to have them. So we'll make sure to follow up on that as well. And with that, I would like to thank you again, Roman, for your time and for your excellent presentation. And I would like to wish everyone a very nice afternoon, and hopefully we'll see you again tomorrow or Friday at the following webinars.
Yeah, thank you, everyone. Thank you, Elke.
Thank you.